last thing we were talking about was the synchrotron radiation. We talked about at the beginning of the acceleration conversation that we needed to have really, really high energies, right? And the reason that we needed to have those energies was what? Why do we need to have high energy?
Have more energy mass. When the collisions occur, the more energy you have, the more possible combinations of particles you get.
Right, right. So the game is that you're bringing this energy mass stuff together. You want the most possible so that you can get the biggest particles out. That is what we are trying to do. So there are two kinds of cases, and we've mentioned them before, but I just want to make sure that we understand the difference. So if you're talking about synchrotron radiation, so the synchrotron is the big one. That's like the Tevatron at Fermilab, the LHC at CERN, right? The big ones where you're actually colliding particle on particle, okay? In that case, so with a synchrotron...
Is that the one where they change the polarity as they go or something?
So they do that both for a linear accelerator and for a synchrotron. So it's the one with the tubes, right?
The one where they change the frequency of it?
Yes, so they have to adjust the frequency because as this thing goes faster and faster, they have to adjust it so that it continues to accelerate it, right? So the tubes are all the same length. Yeah, yeah. So in synchrotron radiation, or in synchrotron acceleration, you have two moving particles. In the other type, so with a linear accelerator or with a cyclotron, they're always fixed target experiments. So you've got one particle moving and hitting something. So the thing that's fixed only has its rest mass energy. It doesn't have any kinetic energy, right, or very, very little. So there's a fundamental difference in the available energy that you have. With synchrotron, you've got, they write E sub A for available energy is equal to, so you've got two particles, and this should be pretty clear about really what's going on. The mass times the speed of light squared, so that's the rest mass energy of the particle, plus whatever kinetic energy you've given it. So if a pair of particles is produced at rest, so part of the nice thing about a particle on particle is that the total momentum of that system is what? Zero, which means that you could produce two particles that are both sitting at rest with a conservation of momentum. Does that make sense? The more, or the slower that the particles that you're creating are moving, I want to make sure I'm saying that in an actual sentence, okay, the more mass they can have. Does that make sense? You have a certain amount of energy. This is the available energy coming in. And if we're going to make something out of that, if they're moving, then some of that available energy has to go into kinetic energy. If they are not moving when they are produced, which doesn't happen very often, but could, okay, this is the maximum possible mass, or, hold on just a second, let me just write that down real quick and then I'll answer your question. And so, is it okay if I write one more thing down? We're never going to produce a single particle. Does that make sense? If you produce a single, there are lots of conservation rules that say we can't produce a single particle. So they're always going to be produced in at least pairs. Okay? And when they're produced in pairs, you're going to have two particles. If they're at rest, each of them would have.
So why can't you produce a single particle? Which laws get violated then?
Well, there would be momentum issues because.
If the total momentum is zero, though, why can't you?
Because the total momentum is never quite zero. Or excuse me, when a particle is produced, it's not produced at rest. Actually, they're going to be moving. Okay. There are also certainly, and I'm not going to, they're not coming into my brain right this second, but there are certainly other conservation rules that would not be conserved, depending on what kind of particle you produce. There are lots of theoretical, like, you know how we can dream up lots of different kinds of particles, but not all of them are theoretically possible. Are you with me there? Okay. And so as a result, the rules say, and this is not a very good answer, Evan, but I'm trying to craft it. It's not physically possible to produce one. I'm trying to develop more than just that. The best reason that I can think of off the top of my head is that they're not going to be produced quite at rest. Let me work on it a little bit more and I'll think about it. Is that okay?
Would
You
other-
suppose? You could look it up too. That would be the other option.
Would other rules be, yeah, this is open source. Would other rules be like the laws that we talked about, conservation laws that we talked about in particle physics?
Exactly. Well, and that's so
And all of that, because you can't.
all of those pieces, right? But if you have, depending on the kind of particle, and that's where I was trying to go with what I was saying, Evan could come up with some sort of crazy particle that where things are conserved, but those particles don't necessarily really exist.
So when you collide those two protons, like a proton and an antiproton or whatnot,
Mm-hmm.
do your point particles don't get destroyed, correct? They just get rearranged, and then you can also create other particles, other like fundamental particles, or like do your quarks get? Do they transform into something else?
Okay, so let's answer that question in a broader way. So well, I don't mean broader way, but like let me get you the answer. At Fermilab, they discovered the top quark. Okay, which means that they had to have seen evidence of the top quark. They're smashing a proton and an antiproton together. Are there top quarks in that system?
I mean,
What's a proton?
No, it's down, no,
two ups and downs.
two ups.
Up,
and
up, down.
Up,
And an antiproton is going to be
anti.
anti of those things. So you've got little quarks, and in that smashing together, right, we see evidence of a top quark.
Right, but does that come from the like transformation of ups or anti-ups into tops? Because that doesn't make sense. Or
Sure.
Does that come from like all the kinetic energy that you give those particles in the collision?
Yes. Both of those things that you just said could happen.
Yes.
So
I wanted to make sure that your yes was that, because that's the yes I was going to say too. Yes. It's a whole big mess of stuff. So it's not like, this is a bad analogy, but I'm going to go with it for now. So my daughter built a tower out of blocks, right? She knocks it over. She builds a new tower. It looks different. Okay? But it's still made of the same stuff. And I think that's what you're asking, aren't you?
well, no, my question got answered. I was just trying to take a little bit further, but yeah, makes sense.
Are you sure?
Yeah.
Okay. Rachel?
So you said 2mc squared is like the maximum mass?
I'm not finished writing.
Oh, okay.
They interrupted me at some point. Let me keep writing. So the mass of the particle, and this is like the maximum possible, right? Is 2mc squared is going to equal 2 of this available energy stuff, or 2e. So the mass of the particle is going to be equal to E over c squared. Go.
Is E sub A for one particle coming in?
No, E sub A is the total available energy.
Then how come it's 2E?
There's two parts.
So this, let me just make sure that I'm saying it correctly. Hold on just a sec, because I feel like that.
Just can.
Let me. I'm just going to read it out loud so that I'm making sure that I make sense. The total energy of the particle-antiparticle pair is 2 mc squared plus ke, where the m is the rest mass and k is the kinetic energy.
This is for the particle antiparticle.
This is for particle, antiparticle. It doesn't matter if they're antis or not, because they're still particles, right?
Right. Okay.
So that's this guy here, okay? The particle with the largest mass that can be produced is given by, well, there have to be 2 of them that are produced, okay?
Okay.
But they're produced.
They're produced in pairs.
They have to have equal mass. So
They don't have to have equal mass.
doesn't that kind of state that they do?
No, they can have different masses and different speeds.
Right,
Like,
right. So
They're restricted
the
to
particle of the
squared.
largest mass that can be produced is given by 2mc squared is equal to 2e.
C squared
Where's two
instead of like
coming
B
from?
squared.
Hold on, I'm reading.
Because I'm kind of trying to relate it back to the book.
Well, but like
No, that's exactly where I'm at. Hold on just a second. I'm just looking here. Plus, the total amount of energy
One to the other.
2E will be available to create new particles.
The available energy is dependent on the kinetic energy.
Right.
Say like momentum isn't zero when the particles are created.
They don't call this E sub A. So I think this is just saying the energy of that particle.
Can have different speeds and therefore different masses.
I think, and I'm not.
So then that E could be different for each
Yeah.
one of the particles.
Yes.
Yeah.
Yeah.
That's what
I think this is the thing that I want you to know for sure. The thing in the yellow box, and let me tell you why I say that. You with me? Are you okay so far? Does this make sense to you? Where this comes from?
Yes.
Is that a convinced yes or a?
You've got two particles, and you add the rest, the energy from their mass, and then the energy from their movement.
Right.
Right.
That's the total amount of energy. This E is not the same E sub A.
And it can be different for each particle.
Right. And this is where, this they don't explain very well. This is what I want you to know.
Yeah.
Isn't it the simplest case though?
Yes.
Well,
This
that
is the
not-
maximum. Very rarely do we have that because usually they fly off, right?
So if that's not the same E, then
What is it?
yeah.
That's a
why
good
are we
question.
talking
And I
about-
don't know, it doesn't say, and that's why I'm struggling.
Oh, okay. I didn't know.
Okay, assume that the particles, antiparticles are both accelerated to the same total energy E. So I think that's just the energy of one particle. I think that's all it is.
Okay.
I think they're just being really, really lazy with their notation. And this is the energy of one particle. So I think that this is really mc squared plus ke of one of the initial particles. That's all I think it is.
Okay.
I think that they're just being really lazy, is the way that I read it.
Okay.
And that makes sense to me.
Yes.
So basically, about half of the energy can go to each particle. It doesn't have to exactly, because momentum can be conserved other ways, right? And energy doesn't have to be, kinetic energy doesn't have to be conserved, right? Because we've got this mass business going on. And so the simplest version would be to say that the mass of one particle would have the same energy divided by c squared of one of the particles coming in. I think that's what they're trying to say.
That's mass of the outgoing particle.
Mass of the new particle that's created.
A new particle. What? Because there's
One of the new particles.
Yeah.
Yes. Each of the new particles.
Okay.
If there are two.
Okay.
Yes. When there are two. Is that okay?
Yeah.
Okay. Thanks for asking. Questions about this? Okay. The second round, the second version, when you've got a fixed target experiment, this one's a little bit different. And this one they explain even less well. So welcome to my world. Yay. So a fixed target, you can do a fixed target experiment with a synchrotron, but it doesn't make a whole lot of sense. But with a cyclotron or a linac, those are the things that you're going to use them for mostly. So this is where you're shooting some fast-moving something at a target. There's a relativity factor that has to be thrown in. And so this is where we say, okay, and we're not going to go through the derivation of where it comes from. This is the available energy expression. E sub A squared, of course, right? Where E sub A is the available energy. Okay. Is equal to, making sure I'm writing this down correctly, 2 mc squared times E. So M is the mass, this is a capital M, is the mass of the target. C, we know, of course, is the speed of light. And this E is the total energy of the particle. The one that's being accelerated, that is hitting the target, okay? Plus big M C squared squared plus little m c squared squared. And little m is the mass of the particle. So the target is like an atom of, or a nucleus of something bigger. So it's not a proton. Okay? Is that okay so far? Yes, that's great, Ms. Carvalho.
It's just because they can't aim it that well to hit a proton.
What's that?
Is that why does it always have to be something bigger?
Well, because the target,
Has to be bigger.
yeah.
They just not that good.
I mean, well, you just put a chunk of stuff there, right? And you're shooting stuff at it, right? So it's not, you're not going to hold a proton there because really a proton doesn't exist, right? So like, yeah, you know what I'm saying? Like, yeah. What?
No, just someone else said I didn't hear that.
It's a cloud of quarks and gluons. That's really all it is, right? Okay.
Why don't we shoot stuff in plasma?
Because we don't have any of that.
Oh yeah, 'cause that's really close to.
We should get some plasma.
So that's not.
You gonna go get some, what?
He's gonna go get some plasma.
Okay.
But
Let me know how that goes for you.
anytime it touches anything that isn't also plasma, it's gonna not be plasma anymore.
That's why.
That's
everything
awkward.
is plasma.
Yeah. Yeah. Okay. So we can play with this idea.
That's great. So you make plasma. If you have a couple of microwaves lying around, get some grapes, put them in there, and it'll make plasma.
Yeah.
That's true.
Although.
Yeah.
Sure.
It's hard to do correctly.
Yeah.
There we go.
Yeah, it has to be a certain type of grape.
That's what I needed.
But you can make plasma, of course.
And
It
I
looks
think
cool.
it's supposed to like make pretty bad
What
gases.
that's
Yeah, it does.
So
It does.
no,
That's
do it
what-
inside.
Yeah, no, you always have to have precautions.
Zero
See?
proton.
Just like when you're gonna throw a battery. Never mind.
You always need to be careful.
Of course, you always have to
Put a battery in the microwave.
No,
What did you throw battery into?
nothing. It's lithium ion.
All right.
Lead acid batteries.
So here's an example. Proton interacts with a, what's that? Negative pion, right? Okay. We've done this reaction, or we've talked about this reaction before. It creates a lambda and a kappa. Were you going to predict it? I'm sorry. Is that what you're upset about?
No, keep on writing A's.
Oh.
Why?
So in this situation, we've got a proton that has been accelerated to some total energy, collides with a stationary pion, and it produces a lambda and a k, or a kappa. Okay. The question is, what is the least energy to which the proton must be accelerated in order to make those two particles? So you probably need some information, right?
Yeah.
What information would you like? What do you need to know?
The mass of
Mass of the stuff.
ion minus the
Yeah.
lambda.
Of all of the stuff.
Everything.
So a pi has a rest energy of 140 MeV. Lambda naught has a rest energy of 1,100 MeV. And a kappa naught has a rest energy of 500 MeV. So then the question is, how much kinetic energy does that little proton need? You can talk that through. What's what? Proton's rest energy is 938. believe. Let me double check here. Yeah.
What are we doing, guys?
Well, then you just find difference in MUDs from both sides and transfer that over to kinetic energy. Because then you're not gonna get an exact answer. 'Cause obviously, your power has different. So you just add like the 14 plus 1100 plus 500. That gets you a 16 14. And you add the 938 plus the 14. And you find the difference in those two.
So you're adding the mass of the lambda to the kappa, right?
Yes. Plus. Yeah.
You're adding another thing to that, or would you be adding?
No, just the lambda and the kappa.
Okay.
And the other side you add the pion for proton. You subtract the two.
All right, so it's 1,078.
So we're using the red equation and then the blue equation, combining those.
You're going to use this equation.
But what's EA?
The available energy.
Yeah, is that what that mean the red equation up above?
No, this is, so the available energy, what you have,
Yeah.
is what can make that lambda and kappa,
Okay.
right? So how much energy, what is the total rest energy for the lambda and kappa combined? It's like 1600, right? So that's what you have to have available in order to create those.
Oh.
What about their kinetic energies though? They're not.
So you just
We're,
solve for-
we want the minimum,
Oh, okay.
we want the minimum kinetic energy that the proton would need in order to create those.
Okay.
Does that make sense?
Yep.
So your 1600 is going to go here.
just
This
solve-
is the mass of the target, so that's going to be the pion, right? That's the pion and that's the proton. And so you're solving for the total energy
You're just solving for the kinetic energy.
and then find the kinetic energy piece of that. So subtract off the rest mass part. Is that making a little more sense? So this would be 1600 squared is equal to, plug that stuff in. Again, like I said, solve for the total energy. But that includes both the rest energy and the kinetic, so you have to subtract the rest energy out. How are we doing? 1,000?
Yeah.
Like 4990-ish?
Yeah.
Something like that?
I got a 2,000.
Yeah.
4992?
Yeah.
Okay. Is that okay? Is that making sense? Okay. I was just looking at the stuff while you were calculating, and I realized that I did misspeak. I misspoke. Did misspeak?
Misspoke.
What if you say did, though?
I did.
Don't say good.
I did misspeak, yeah.
Thanks, Harry. stuck in a situation where we sent it. I don't know. Yes, the question was, can you shoot one particle at something like it? And yes, you can. I was thinking bigger picture, like the one that we had seen before, the one that we saw at Fermilab, where they were shooting at really big targets. Often, fixed target experiments, like with a cyclotron, and I hadn't really been thinking about cyclotrons, they will shoot like a proton at another proton. I misspoke about that. So they often will take this equation, and I want to tell you this because we're going to try a couple problems with it, and they will simplify it, right? Because then this m and this m are the same. So if the target and the accelerated particle are the same, then you can say that EA of it, like so the available energy squared, is 2 mc squared E plus, twice mc squared squared. So that's just adding those last two terms together. Okay. And then they say one more thing. By the way, often the bombarding particle is really, really fast. And so if that's the case, and this I think is kind of a little hand wavy, but we'll write it anyway. If the accelerated particle is fast, like really fast, then you can make an approximation that EA is really just equal to the square root. So we get rid of the rest mass relative to the total energy, and so it's just 2 mc squared E. So this is a big approximation, but the book says, furthermore, if the bombarding particle is really fast, I think that's kind of a cop-out, honestly. I would use this one here.
How fast is really fast?
Right, that's
Speed of light, like.
exactly. That's why I don't like that statement. I want to make sure that you've seen it, so that if there was a statement on a test, right, that had like started you here, and it wanted you to get there, you wouldn't be scared of getting there, right? Because the rest mass is not very big compared to the total mass. Fair? Okay. Like I said, I don't really like it, but it is what it is. Turn to page 739. I want you to try a couple of these problems just to make sure that these things are good, because I see a lot of problems like this on IB tests, and I want to make sure that they make sense. If you need a sticky note, then let me know. Otherwise, I'm guessing some of them have them in there. I'd like you to work on Q2 and Q3. Why don't you work on Q2 and Q3? You need a sticky note? I'll get you one. Hold on just a second. Page 739, 740, Q2, and Q3.